Another example to have a go at with integration by parts is the one you see here, where you've got x squared e to the x. So what we're going to do is we're going to learn from our previous examples, which is how do we choose which function we choose as u and which one we make our d dx. So if we just set up our problem, what we've talked about in the past is that if we can reduce a function to a simpler function by finding its derivative, knowing what our formula is, then that's the one we choose for our u. So in this case, e to the x doesn't simplify at all. So it's easy to integrate or differentiate, but it doesn't simplify. So we're going to use it to help us by choosing x squared as our u. So if we find the derivative of x squared, that becomes 2x. So it's simpler. Let's see what happens. So we integrate, so remembering, actually, our formula is u v dx is equal to u v minus integral of v du dx dx. So putting in our values, so we've got x squared e to the x, that's going to equal u, which is x squared plus v, which is e to the x, minus integral of v, which is e to the x, times du dx, which is 2x dx. And what you notice, I'll just rewrite that a little bit, so x squared e to the x minus 2 times integral of x e to the x. And we haven't actually got to a point where we can integrate yet. So in this particular type of example, what we're going to do is we are going to use the integration by parts a second time. So we're going to set it up this time. This time u is going to be x, the v dx. Oops, the v dx will be equal to e dx, and we just go through to u dx is equal to 1, and v is equal to e dx, just like it was before. And then we can continue. X squared e to the x minus 2, and then we're going to have uv minus, so it's the same process, u times v minus the integral of v, which is e to the x, times du dx, which is 1. So now we're at a point where we can integrate. Oops, put the bracket in. So we've got x squared e to the x minus 2x e to the x. Then the negative 2 times the negative sign will become plus 2 integral of e to the x, e to the x, plus c. And we can take out a common factor, because we always like to factorise, x squared minus 2x plus 2 plus c. And there's our solution. Okay, and that was where we sometimes have to use the, we sometimes have to use the integration by parts twice. Now, an alternative version of that is a problem where you might get something like this. So find the integral of e to the x cos x dx. So it's similar to the previous example where we've got e to the x, because e to the x is a really useful one to do with integration by parts because it differentiates and integrates to itself. But the cos doesn't. It's not going to reduce. So what do we do in this situation? Okay, so what we're going to do is we're going to let u be e to the x and the v dx, whoops, pen's decided not to work, the v dx equal cos x. Therefore, the u dx will be e to the x and v will be sin x. The integral of cos is sine. So, keep going in the blue. So the integral of e x cos x is going to be u times v sin x minus integral of v sin x times e to the x dx. Okay? And so we look at that and we think, well, how have we solved that? So I'm just going to, what I'm going to do right now is I'm going to write that whole line out. Okay? I'm just going to write that line out so it's all in one line, because that'll become easier when we get to the next part. Sin x minus the integral of e to the x. I'm just going to rewrite that in that form. All right. So if you have a look, what we've got in the integral back here is very similar to what we started with. So what we're going to do is we're going to do the same process. Okay. So we're going to go u is equal to e to the x and dv dx is equal to, in this case, sine x. So we're going to try again. So du dx will equal e to the x, and v will be minus cos x. So now we're going to have e to the x sine x minus bracket uv, so u times, so e to the x times minus cos x, so we'll tidy that up in a minute, minus the integral of v, which is negative cos x, times du dx, which is e to the x dx. Okay, so let's just tidy this up a little bit. So equals e to the x sine x. Now the two negatives will become plus e to the x cos x. And then those two negatives will cancel. So we're going to have plus again. Although in this, oh yeah, so we're going to have plus integral e to the x. Whoa, what's going on here? Pen's dying. E. I wrote plus there, but it's actually a minus, and I'll show why. So we've got two negatives in here, but we've got the negative outside the brackets as well. So that actually is going to remain it to be a negative. What? No pen. So that's actually going to be a negative. Let's make that a bit neater. E to the x cos x dx. So it looks like we're back to the start. What we actually have is a situation where we've got an e to the x cos x dx on the left-hand side of the brackets, the equal sign, sorry. We've got an e to the x cos x dx on the right-hand side. So I'm going to move all of this term here to the other side of the equation. So what I'll end up having is the integral of e to the x cos x dx plus the integral of e to the x cos x dx, which is in fact 2 times the integral of e to the x cos x dx equals e to the x sine x plus e to the x cos x. Okay? Remembering what I want in the first place is just the e to the x cos x. So I've got one on both sides. By moving it to the other side, the negative becomes a positive. And I've got two of them. So if I get rid of that 2, e to the x cos x dx, which is what I want, is going to be a half, divide both sides by 2, e to the x, and then I'm just going to collect like terms, plus c. And there's my solution. So sometimes in these examples, you have to do the integration by parts twice, and it simplifies down to the fact where you can actually take an integral, like we did in this example. And sometimes you have to do the integration by parts twice, sometimes 3 times, but you don't simplify down, but what you end up with is what you started with, or what you want in the originally, and then you can collect those together and find your integral at the end.